Hi, this is a video about how to draw molecular structures. It is lesson 3, module 7. We won't really be using, the textbook teaches us a little bit differently, so I am just directly teaching this. So when we talk about covalent bonds, we are going to be using structural formulas. And sometimes, this is the Lewis structural formula that we're really going to focus on. And these other space filling and ball and stick ones are interesting, especially when we're using the PhET and looking at different shapes and molecular polarity eventually. So these are the steps, and it looks kind of daunting, but these are the way, if you do these steps in order, then you should be successful in drawing Lewis structures. This is different probably than if you previously learned this in physical science. So definitely recommend that you do it this way, and then all of your diagrams should work out. So first thing you do is you predict the location if you have more than 2 elements. The one that has the lowest electronegativity will be the central atom. And then you want to count all the valence electrons available, so every element that's in the structure, their valence electrons. We call that electron cache. Then you want to draw single covalent bonds and use lines to represent every 2 electrons. Then you subtract those from what you had, the total electrons. Then you're going to add the remaining electrons to the outside, not to the central atom, unless you have enough. And then lastly, you'll look at the octet rule, rearrange electrons if needed, with forming double and triple bonds. So we'll just do some examples. So here's fluorine gas, F2. So fluorine, there's 2 fluorines, and each fluorine has 7 valence electrons. So we have a total of 14 valence electrons, which we're going to call that the electron cache. So then the next step is we're going to put, this one isn't too hard because there's only 2, so we don't have to determine a central atom. But this is a single covalent bond that represents 2 electrons. So I've used 2. I'm going to subtract those from the 14, which means I have 12 left. I want to place them in pairs around the fluorines until I satisfy octet rule. So you can see that by doing what I just did, there's 2, 4, 6, 8. So I want to move on. That fluorine is good. And then I still have 10, 12, 2, 4, 6, 8. Oh, sorry. And I'm placing these 12 electrons. So 2, 4, 6, 8, 10, and 12. So, and both of the fluorines are satisfying the octet rule. Let's show you another one that's a little bit more complex. So this is ammonia, and ammonia is NH3. So nitrogen and hydrogen. We know we have 1 nitrogen, 3 hydrogens. Nitrogen has 5 valence electrons. Hydrogen has 1. So that gives us a total electron cache of 8 electrons. Central atom is, this time, if you go with the least electronegativity, then you would pick wrong. You can kind of see from the structure that nitrogen is going to go in the middle. Just hydrogen only bonds once, so it can never be the central atom. So I would draw N with single covalent bonds to the hydrogens. So remember, each bond is representing 2 electrons. So had 8. Now I've used up 6, so I have 2 left over. And I'm not going to place them on the hydrogens because the hydrogens are already stable. They don't have an octet, but they have 2 electrons, which is like helium. So they are just fine. So these extra 2 electrons are going to go here. And then you can just evaluate. Nitrogen has 2, 4, 6, 8. And then each of the hydrogens has 2, which is stable. So let's look at another one. So this one is SCl2. And again, you can see sulfur does have the lowest electronegativity, but also kind of from the formula, you can guess that sulfur would be the central atom. So if we calculate the cache, we have 2 chlorines and 1 sulfur. Sulfur has 6 valence, chlorine has 7. So we get a total of 20 electrons for our electron cache. So this one, I'm going to put the sulfur and draw those single covalent bonds. So remember each line is 2 electrons, so I've used up 4. So now I have 16 electrons left. So here's where one of the rules we haven't really applied yet is we're going to place the electrons around the outside atoms, so the chlorines, and then the central atom if we have enough. So I'm going to place 2, 4, 6. So now that chlorine has 8. So there's 6 of the 16, 8, 10, 12. So that chlorine is now good. And now I can place electrons on the central atom, which would be 14, 16. So this, if you evaluate it, each element has 8 valence electrons. So now let's start talking about some of the multiple bond cases, and this typically happens with carbon, nitrogen, oxygen, sulfur. So you're going to still do the same process. So carbon dioxide, we have carbon and oxygen, 1 carbon, 2 oxygens, 4 valence electrons for carbon, 6 for oxygen, which gives me 16 total valence electrons for my electron cache. So again, I'm going to put carbon in the middle, lower electronegativity, and then now you can see I've used up 4 electrons with those 2 lines, those single bonds, each have 2 electrons, which gives me 12. So what I'm going to do is I'm going to place those around the outside first. So 2, 4, 6, 8, 10, 12. Then I evaluate, and I can see that oxygen, the right oxygen has, sometimes I do a smiley, but it can be confusing because there's electrons, but that oxygen is stable, satisfying the octet rule. So is this one. Carbon, however, is not. So carbon right now only has 4 valence electrons. So what happens is we're going to rearrange electrons. So the oxygens can share. So that pair of electrons now we can put into a double bond. And you can see this oxygen here has 2, 4, 6, 8. It's still stable. Carbon now has 2, 4, 6. It's still not stable. So now this other oxygen can lone a pair. And then now my carbon has 8. So 2, 4, 6, 8. So everyone has 8 valence electrons, and that is the structure for carbon dioxide. Polyatomic ions, drawing these, you still follow the same rules. The only thing is you look at the charge of the ion. If it's negative, you're going to add that many electrons. If it's positive, you're going to take away as many electrons as the charge. And then also we place brackets around it just to differentiate it from something that's neutral. So example, PO4 phosphate. So P and O, there's 1 and 4, 5 electrons, and 6 valence electrons. So we get 29, but we have a charge of -3. So we're going to add 3 more electrons, which is going to get us to 32. So this is our electron cache. We're going to put P phosphorus in the middle, put the oxygens on the outside. So you can see I've used up 8 electrons. So now I'm left with 24 electrons. I'm going to change to a different color just so you can really see. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So it worked out. The only other thing, everyone has 8. The additional is that you're going to write the brackets around and then also the charge. So -3 would go still as a superscript. So resonance happens when you can draw more than one Lewis structure for something. A lot of times there's sometimes 3 different ways to draw it. You don't have to draw all the resonance structures. I just want you to appreciate it. So for example, nitrate, they draw it a little bit like we probably would have drawn it, straight across. It's same thing, so we could, and then nitrate is an ion. We could place that double bond really in any one of these 3 spots. And in reality, they're all correct structures, and the electrons really kind of go in between all 3 positions, which you can't really show on paper. So for us, if you see a resonance structure where you draw it and it might be a little bit different than me, you can let me know and I can just double check that that it's acceptable. So you don't have to draw all 3, you can just pick one, but it might be different than the one that I choose. And that is